So we talked about enthalpy, and basically, again, a measure of the transfer of heat, and it is defined at constant pressure. And if we are operating at constant pressure, then delta H equals Q. And for all of our purposes, until we talk about bomb calorimetry, that will be the case. There are lots of ways to express Q and H for that matter. So sometimes you might just see Q, or we might label it Q of the water or Q of the metal. Depends upon what kind of calculation we're doing. Q of the reaction, Q of the solution. This is just telling me something about the type of reaction that's occurring. And so we can also delta H of a reaction, for example, delta H of solution, delta H of vaporization. So there are other ways to label delta H as well, is all I'm trying to say. And again, I've mentioned that these delta H's can be looked up in a table at the end, or an appendix at the end of the chapter. And those delta H's are given as in kilojoules per mole. So make sure you're careful when you're doing conversions that you're paying attention to units, because all of our Q calculations end with an answer in joules. Okay. But there's a slide here, and it tells us, or at least is a practical application, I should say, of why we care about delta H's. So for calcium chloride, the delta H of solution is minus 82.8 kilojoules per mole. So what else did we learn about delta H and signs of delta H and Q last week? Delta H is negative. What does that mean? What kind of a reaction do we have? It's exothermic. So that's exothermic. And I'm taking these from the table. Ammonium nitrate has a delta H of 26.2 kilojoules per mole. So this, and these are heats of solution, I should say, delta H solution. So when this dissolves, it's an endothermic reaction. So one of the things you'll do today in lab, when you first you'll calculate the specific heat of a metal, and then you will determine heat of solution. And some of you will have compounds that transfer heat, the reaction of dissolving transfers heat to the water, and your temp will go up. Others will have compounds that are endothermic, and your temperature will drop. But keep in mind, when you are calculating Q, you are calculating negative Q of the water. So Q of that reaction, or Q of solution, or whatever it is we're dealing with there. Okay? All right, now we're going to talk about thermochemical equations. And we're going to look at, I think we'll look at this two ways, actually. Here's just a phase change. So we have solid water being converted to liquid water. And so phase changes are thermochemical equations as well. We can write reactions as thermochemical equations, but also phase changes. They have delta H's associated with them. And when we write a thermochemical equation, we also include the delta H for that process. And this is more specifically the delta H of fusion. So to melt ice, is this process exothermic or endothermic? Endo. It's absorbing heat from the surroundings. Okay. The reverse process, if we are freezing, so this is the opposite process, what would its delta H be? But what's its delta H?
-6.
Correct. Delta H here is negative 6.01 kilojoules. So anytime we have opposing processes, if you looked at condensation and evaporation last week, the value of delta H will be the same, but the sign will change. It will have an opposite sign. So this is a simple way to use some of this delta H data. For example, we have a thermochemical equation. We have P4 solid plus 5O2 gaseous, giving us P4O10 solid. And the delta H of this reaction is negative 3013 kilojoules. And that's per mole of P4. So what kind of reaction is this? Even though it doesn't look like one with respect to products. Oh, it is exothermic, but what are we doing? Are we burning here? Actually, we are. We are. Yeah, it is burning. Yeah. This is actually the white light and fireworks. So that white flash, that reaction. But anyway, that's not the... My question is, how much heat is evolved when 266 grams of white phosphorus, and that is what P4 is commonly called, burn in air. So here I'm going to use delta H as a conversion factor. And this is another comment I meant to make, and I'll come back to it in a minute. So we're going to start with our mass of P4, and we're going to convert that to moles. So we'll need molar mass of P4, and that's 123.9 grams. And then I can use my delta H as a conversion factor. Per 1 mole of P4, I generate 3013 kilojoules of heat. Now I want you to notice the sentence used the word evolved. And that tells me I know that it's exothermic, and I'm just going to give the value without a negative sign. And so what this turns out to be is 6470 kilojoules is generated by that mass of P4. We require 3 sig figs here, which means I have to put that in scientific notation. And that is the amount of heat evolved or given off by that process or reaction. So next we're going to look at 2 ways to calculate delta H. One is a direct calculation, and actually I'm going to say this and then I go back to what I meant to follow up with. And one is an indirect method. And next week you're going to be using the indirect method to calculate delta H of a reaction in your lab. But what I meant to say was there were some exams that students used a mathematical approach to their worked problems, and that doesn't fly. You need to show me the correct setup with your units canceling. And I've noted on those exams that next time there will be 0 credit. You need to do it my way. The chemistry way. So, if you have questions about that, come and see me. So, moving forward. So I have to define something we call the standard enthalpy of formation. And it is represented by a delta H, a superscript naught, and a subscript F for formation. So standard heat of formation. This is basically an arbitrary scale, and it uses sea level as a reference point. And by definition, it is the heat change. That results when 1 mole of a compound in its most stable physical state is formed from its elements. In their most stable physical state. Okay. So by definition, any element in its most stable physical state has a delta H of formation of 0. So for example, the delta H of formation of O2 equals 0. Standard heat of formation for H2 is 0. Those are the most stable physical states. And I can compare the delta H of ozone to O2. So ozone is not the most stable physical state of oxygen. This has a heat of formation of 142 kilojoules per mole. Another example, standard heat of formation of carbon in the form of graphite, which is its most stable physical state, is 0. But the standard heat of formation of carbon in diamond has a delta H of 1.90 kilojoules per mole. So if you do enough of these problems, you'll, figure out what's the most stable physical state of some of the more common elements or diatomic molecules. But as you start out, I highly recommend looking them up. Also, with respect to water, depending upon its physical state, there are going to be different delta H's. So you need to pay attention to the physical state as well when you look those up. So how do we use that? So the direct calculation of delta H using standard heats of formation is standard heat of reaction equals the sum of the standard heats of formation multiplied by a coefficient, if there is one, of the products minus the sum of the standard heats of formation of the reactants. Oops. So this is a generic representation of a reaction where the lowercase letters are the coefficients, of course. And if I wanted to write the standard heat or the generic standard heat of reaction equation for this, it will be C times the standard heat of formation of capital C. So this is the N plus the D coefficient times the standard heat of formation of D minus A, standard heat of formation of A plus B times the standard heat of formation of B. And I look up those standard heats of formation. Yeah, we'll see how this goes. So I want to point out another way to write a thermochemical reaction. And so I think we'll start with a new paper here. Oh, I'm sorry. Sorry. Maybe I'll stay here for a moment. So I have this reaction. And we're reacting nitrogen and hydrogen to form 2 moles of ammonia. And the delta H, or the standard delta H for this reaction, is negative 92.2 kilojoules. This is a thermochemical equation for the production of 2 moles of ammonia. But there's also something called a formation equation. We will only work with these equations, but you need to be able to recognize a formation equation. So a formation equation is for 1 mole of product. So this is going to be an exception with respect to the rule that we don't have fractions as coefficients. Because to write the formation equation for this reaction, we have to divide every coefficient by 2. So the formation equation for 1 mole of ammonia is 1/2 N2 plus 3/2 H2. Yep. I'm sorry, what?
The coefficient of hydrogen and ammonia.
Yes. Oh, I didn't put the 3 there. Sorry.
Yeah.
Oh, thanks. Yeah. 1 mole of NH3. So this was delta H of the reaction. This is the standard heat of formation for ammonia. And when I divide those coefficients, I also have to divide that delta H. So this delta H of formation is minus 46.1 kilojoule. And that's per mole of ammonia. Oh, yep, Alicia. Why did I divide it? 2. Because I have to divide every coefficient by 2 to get this 1 mole, to get this to be 1 mole of ammonia. Okay? So the formation equation is per 1 mole of product, but whatever I do to that thermochemical equation, I have to do to delta H. And that's going to be important when we introduce the next way to calculate delta H, and that is using Hess's law. So if you recall, we talked about state functions, correct? What does that mean? And we talked about what types of properties have our state functions: temperature, volume, pressure, enthalpy, delta H. Okay. So if you remember that slide, there were 2 hikers. One went straight up the mountain, one meandered all the way to the top. They both started with the same amount of potential energy, and when they get to the top, they have the same amount of potential energy. Doesn't matter what the path was that they took. And that is what is applied in Hess's law, which is the indirect method. Of calculating delta H. And this breaks the process up into steps. And there is an example. Let's see. There we go. Of that for the formation of CO2. We can combine 2 different reactions to come up with the formation of CO2. And here we have C graphite plus 1/2 O2, giving us carbon monoxide, and this has a standard heat of reaction of negative 110.5, and these are all in kilojoules, just just write that at the top there. And the other equation I have is carbon monoxide then reacting with a half a mole of oxygen to produce CO2. And the delta H for this reaction is negative 283.0. So basically what this is going to involve is manipulating some given equations, and I'm just showing you an example without giving you the equations first, but you'll have to manipulate them and then sum them together in order to come up with the overall reaction. And we likely won't get to do one of those today, other than taking a look at this one. So, we are going to cancel anything that appears on the left-hand side in one equation and the right-hand side in the other equation. Okay. What do you see that could be canceled? Nope, they're both on the left-hand side. They have to be on opposite sides of the arrow. Carbon monoxide is on the right in this equation, is on the left in this equation, so they cancel. And then I'm going to add these together, because that's all that cancels. So I have C graphite plus O2 gaseous, giving me CO2. And I add my delta H's together for that reaction. So the standard heat of reaction for this process is negative 393.5 kilojoules. No, they have to be the same physical state. Yep. You what? They're both. Oh, I'm sorry. I'm forgetting subscripts here. Sorry about that. It's O2. Thanks for pointing that out, though. So I also could have calculated this directly by looking up the standard heats of formation. We'll do many more of these, so don't worry. And I'll try to not forget subscripts. So we could have directly calculated it by looking up those standard heats of formation. And for this reaction, it would have been, or it is, N times the standard heat of formation of CO2 minus the sum of N times the standard heat of formation of carbon in the form of graphite plus N times standard heat of formation O2 gaseous. We just covered the fact that carbon in the form of graphite is in its most stable physical state, and O2 is the most stable physical state of oxygen. So I know those are going to be 0, but again, you should look these up initially. But I did look up that the standard heat of formation of CO2 is negative 393.5 kilojoules per mole. I have only 1 mole. Those cancel. And these were 0, so subtract 0. So my standard heat for this reaction is negative 393.5 kilojoules. So you should get the same answer. Doesn't matter which approach you take, but you will be required to be able to use both processes. Okay? And that's all for today.